Good day, everyone. Today I'm going to talk about how to quantify the uncertainty of image labelings using assignment flows. This work was done in collaboration with Alexander Zeilmann and Christoph Schnoerr from the Image and Pattern Analysis Group at the Heidelberg University. In this talk, I will mainly focus on the image labeling approach, where the task is to label an input image using predefined prototypes. Pixelwise image labeling is of utmost importance in many applications. However, equally important is the confidence in the labeling result, which means quantifying uncertainties estimated at the same time. We would probably all agree that deep networks define the state-of-the-art approach for image labeling. However, they tend to be vulnerable to small modifications of the data. For example, we can see here that even for these two images that look the same for the human eye, the network performed two different classifications. It is fundamental in many applications to evaluate the efficacy of the system before its usage. So what we would like to have is a quantitative uncertainty of each single test sample, rigorous mathematical derivations based on the labeling approach, and of course, feasible computations. We will solve this by using assignment flows as a labeling tool. Assignment flows were proposed 4 years ago in our group as a geometric variational approach to handle the labeling task. Assignment flows are smooth dynamical systems that involve a statistical manifold. This manifold, which we call the assignment manifold, is the Cartesian product of probability simplices, as many as pixels we have. Sadly, I don't have the time to explain this approach now, but very briefly, data is lifted to the assignment manifold and drive the dynamical system that we solve numerically in order to obtain the image labeling. Here below, we can see the most simple scheme of geometric integration, and very roughly speaking, it involves the two basic ingredients of deep networks. First, we have here pointwise nonlinearity, and second, we have here convolution-like spatial interactions. Regarding related work, I just would like to refer to this recent survey of uncertainty quantification in deep learning, with about 700 references. They also report that over the past 10 years, more than 2,500 papers were published linking uncertainty quantification with deep networks. This shows, of course, the relevance of the topic. We observe in most of these works absence of theory, sensitivity to imperfect data, and expensive computation. In contrast, our approach to be introduced now enjoys the favorable properties mentioned before. Our approach, which solves the labeling task, allows us to quantify the uncertainty of final labelings. To this end, we first extract local uncertainty information from the input data and push forward this information to the tangent space of the assignment manifold. We then use a linear parametrization of the assignment flow and study how the uncertainties propagate. I will first explain how we estimate the local initial uncertainties, and afterwards I will move and show how to study the uncertainty propagation. In order to determine the local initial uncertainties, we apply for every pixel local geometric averaging around its neighborhoods. These deliver local data variations, which are points in the probability simplex. We consider them as samples of Dirichlet distributions. We do it so since Dirichlet distributions are standard parametric measures supported on the probability simplex. We later exploit the statistical information of Dirichlet distributions as exponential families and estimate the parameter which best fits these initial uncertainties by maximum likelihood estimation. This is a convex program which we solve with standard convex programming methods. Afterwards, we lift the first and second initial moments to the tangent space and use the vector space structure to study the moment evolution. The next step consists in studying how these initial uncertainties evolve along the assignment flow. For this, we first consider a linear ODE parametrization of the assignment flow. We consider for every pixel the initial values of the ODE as normal distributions. To be more precisely, since the covariance matrices are singular of corank 1, we are handling here with intrinsic Gaussian Markov random fields of first order. We further assume that these initial moments are identically independently distributed, which lead us to a Gaussian random process. Due to the linearity of this parametrization, it is sufficient to just involve this moment to understand the whole process. Thus, we get a very specific case of the general Fokker-Planck equation, which we later solve. The concrete numerics of the formulas written down here require the evaluation of the matrix exponential followed by a matrix vector multiplication. Thus, they might look computationally expensive. However, using Krylov methods, they can be approximated quite efficiently. As proof of concepts, we show that uncertainties are large where we expect them to be large. In the top row, we see a noiseless image. In the top center, we see the local initial uncertainties estimated from the data. We can see that uncertainties are located at the signal transitions. On the right, we see the uncertainties are very low, almost zero, because there is no noise due to the regularization properties of the assignment flow. In contrast, in the bottom row, we see the noisy scenario. We see in the center dramatic local uncertainties, and on the right, that even after the regularization, some uncertainties remain at the signal transitions. Summarizing this work, we introduce a novel approach for quantifying the uncertainty of image labelings using assignment flows. We first model initial uncertainties using Dirichlet distributions, and afterwards, we study the moment evolution using a linear parametrization of the assignment flow. We validate our result with proof of concepts experiments. Our further studies will concern in studying the effect of regularization parameter learning of the linearized assignment flow and to extend the study to general assignment flows. Thanks for your attention. Now I would be very happy to take any question.